Today's lesson is twofold. One, we're going to understand what's the difference between a molecular formula and an empirical formula. And the second part is we're going to use the percent composition to determine the empirical formula. Now, if you already know what an empirical formula is and a molecular formula, you can skip to about the middle of the video and that'll tell you how to do the percent composition to molecular formula technique. If not, just start watching from the beginning of the video. So the difference between the two formulas is this. The empirical formula shows you the smallest whole number ratio of atoms in the compound. You can think of it this way. It cannot be further reduced to a smaller whole number ratio. So for example, and we're going to look at these two compounds here, NO2 and H2O, can we further reduce the subscripts to a smaller whole number ratio? And the answer is no, because we have one nitrogen and two oxygens, and you cannot further reduce one to make it a smaller number for the ratio. And the same thing here is we have two hydrogens for every one oxygen. So we are in the simplest form right now. The molecular formula will tell you exactly how many atoms are present in the molecule. Now note, the molecular formula can also be the empirical formula, and we'll show that in a minute. So let's look at these two examples right here, H2O2 and N2O4. Now, can we further reduce H2O2 to a smaller whole number ratio? And we can. If we divide each one of the sides by 2, and remember you've got to divide each side by 2 to keep the ratio together, then you would get HO. And that would be the empirical formula because that shows you it's a 1 to 1 ratio. And that's what it is here. It's a 2 to 2, 1 to 1, same thing. Now, for example, N2O4, let's look at that one. Can we further reduce it? We can. So if we take each side and divide by 2, remember we have to divide each element by the same number, otherwise you're going to destroy the ratio. The ratio here is 1, and then we get a 2 here, so it's NO2. And so that would be the empirical formula for N2O4. So again, many compounds can have the exact same empirical formula, but each has a different molecular formula. So here we go. We can look at all of these materials here. C2H4, C3H6, C4. They all have a 1 to 2 ratio. So for every 2 carbons, I get 4 hydrogens. So if I divide this by 2, I get a CH2. If I divide this by 3, both sides, I get CH2 again. And this by 4, I get CH2 again. So they all have the same empirical formula, but they have different molecular formulas. And that's the difference between the two. One is the empirical formula cannot be further reduced into smaller whole number ratio. The molecular formula just tells you exactly, and the key word is exactly, how many atoms are present in the molecule. It may or may not be the empirical formula. For example, H2O is an empirical formula because it can't be further reduced. It's also the molecular formula for water. Okay, so let's see how you do on mastering that concept. You're going to now stop the video when I tell you to and copy these down, and then you're going to write empirical or molecular. If it's in a molecular formula, you're going to then further reduce it until you get to the empirical formula. Now, if you think it's both, you're going to write not only E, you're also going to write B. Because I want to know if you know it's an empirical formula, and then you also know that it's also a molecular formula. So if you think it's both, write E and B. If you just think it's a molecular formula, you're just going to write M. If you just think it's an empirical formula, you're just going to write E. So the only one you're going to write 2 letters for is if you think it's both. So stop the video now. Okay, so here are the answers, and we already went over through the H2O one right here. H2O2, we did that one on the other page. N2O5, can we further reduce that? We cannot. So we could divide each side by 2, but then we get 5. 5 divided by 2 is 2.5, and 2.5 is not a whole number. Here we have C6H12O6, and the common factor would be 6. So if we divide everything by 6, we get C1. This would be now a 1. There would be a 2 here, and this would be a 1. So the way we write that would be this. C2H4 we can divide through by 2, and we get CH2. Now, note, you cannot divide through by a different number for each side. For example, if I divide this side by 2, I have to divide this by 2. You've got to keep the ratio the same. So the ratio doesn't change if you divide by each side by the same number. You couldn't divide this by 2 and this by 4. Right? So you have to divide each number by the same number if you're going to further reduce it. So that's how you get that. PI3, this is a 1 and a 3, and I told you anytime that there's an element in a formula and it's only one of them, then you, by definition, have to have the empirical formula. Okay, so some more practice here. You're going to tell me which of these is not an empirical formula, not an empirical formula. So what you're going to do is you're going to stop the video when I tell you to, and then you're going to copy these down or do some scrap work on your side paper, and then tell me which is the correct answer. So stop the video now. Okay, you should have gotten that this is the correct answer. Now, why aren't these other ones correct? Well, again, you may have to be able to reduce both things by the same amount. So if I take this and divide by 2, I get a 1 and then a 1.5, and 1.5 is not a whole number. If I divide this by 3, if I make that a 3 now, I get 0.67 and then 1. And again, this is not a whole number. 0.67, not a whole number, not a whole number. All right, next one, 2, 8, and 1. Now, it might look here and say, oh, I can divide by 2. But you can't, because don't forget, that's a 1. So even if you divide it by 2 to get the further round, you get 1, 4, and then 0.5. And again, 0.5 is not one of the answers. This one, everything can be divided by 2 to get this. And the last one, again, we have a 1 there. So by definition, if you already have a 1, then you have to have the empirical formula is already listed. It could be also the molecular formula, but I'm asking you here just specifically if it's an empirical formula. Now it's asking you which one of these has the same empirical formula. So I'm going to stop the video, have you stop the video, work the problem out, and then start the video again to get the answer. Now I'm going to give you a little hint. Right? In order to have the same empirical formula between two compounds, not only do you have to have the same ratio of elements in the compound, you actually have to have the same elements in the compound. So knowing that, move forward on with that information and solve the rest of this. So you should have one answer by the end of this. So stop the video now. Alright, so here's the answer, and as I said before, you've got to have both elements the same. So we have a carbon here and a sulfur here, and so they're not the same. So not same. Therefore, even though we have a 1 to 2 ratio, they're different elements. So that's out. We're going to skip the answer real quick. C4H10 and C10H4. Well, they look like they have the same ratio, but this one it's 4 carbons to every 10 hydrogens, and this one it's 10 carbons to every 4 hydrogens. So that ratio is different. So that's out. Even if you further reduce it, you're going to see that if you further reduce it and divide this by 2 and everything by 2, these are not the same. C6H12 and C6H14, well, the carbons are the same, but the hydrogens are different, therefore the ratio is different. So again, when you further reduce it to get the empirical formula, these are not the same. So the only answer is this one. And you can see here, if I divide this side by 7 and this side by 10, you don't have to, because they're different compounds, you're going to get CH2 and CH2. So here's the connection between the number of moles and the subscripts in a chemical formula. The subscripts tell you the number of moles of that particular atom in 1 mole of that particular molecular species. So for example, aluminum oxide has 2 moles of aluminum atoms for every 1 mole of aluminum oxide, and 3 moles of oxygen atoms for every 1 mole of aluminum oxide. And you could do the same thing here. 1 mole of phosphorus atoms for every 3 moles of iodine atoms for every 1 mole of phosphorus triiodide. So we're going to use this information to help us go from moles to empirical formula to grams. Okay, there's a lot of words on this page about the steps involved, but they're fairly straightforward once you see it. So before we went from a formula to a weight percent composition, and now we're going to go the opposite way. We're going to take a weight percent composition and go back into the empirical formula. And so we're just going to do the steps in reverse of what we did before. So first of all, what you're going to do is you're going to assume you have 100 grams of the substance. You're going to replace the percentages of each one of the components. Instead of the word percentage, you're going to write grams. So if you have 50%, you're going to say it's 50 grams. You're going to convert that back into moles using the molar mass conversion. Then you're going to divide through by the least number of moles for all the materials to get a whole number ratio. And then if your whole number ratio is within 0.1 for each subscript, then you're going to assume that that's close enough. If not, you're going to have to multiply it by a factor. So let's see how it works on the next page. Okay, so a compound containing sulfur and oxygen is analyzed, and it has 50% sulfur by weight and 50% oxygen by weight. So what is the empirical formula? So all we're going to do now is we're going to say, okay, I have 50% sulfur. So here's my 50% sulfur. And then we're going to convert the 50% into 50 grams, and that's that right there. Then what we're going to do is we're going to say, well, how much oxygen do we have? So we have 50% oxygen. That converts to grams, and that's that there. So we've done step 1. Okay, so now using the molar masses of each one, we're going to convert to moles. So we've taken that 50 grams, and remember, this number here is the molar mass of sulfur, and this number here is the molar mass of oxygen. You look that up in your periodic table, and you convert to moles, and then when you do that, you get, for the first one, you get 1.56 moles of sulfur and 3.125 moles of oxygen. So the molar ratio in the compound is 1.562 to 3.125. Now, that is not a whole number ratio, so we're going to have to convert it to a whole number ratio, and we'll do that on the next page. Okay, so now that we have the molar ratio, the moles of each thing, we're going to now convert it into a whole number ratio by dividing the smallest amount to normalize the ratio. So I look at my things here, and I see that 1.56 is smaller than 3.125, so I divide everything by the same number, which is the 1.526, to get a ratio of 1 to 2. So it's telling me that I have 1 mole of sulfur atoms for every 2 moles of oxygen atoms. So in my formula, it would be S1O2, and we don't write the 1, so it would just be SO2. So again, you're going to divide through by the smallest number of moles that you calculate to normalize everything. Okay, so let's say you do all the steps, and at the end you get these numbers right here, 1 and 2.5. And so you say to yourself, well, that is not a whole number ratio. 1 to 2.5 is not a whole number ratio. So what am I going to do to get it into a whole number ratio? Well, the thing I have to do is I have to multiply it by a factor. right? And that factor you multiply by to get the decimal one into a whole number ratio is going to be the same for everything that in that compound. So if you multiply this by 2 to get 5, you have to multiply this, whatever this number is, by 2 also to keep that ratio the same. Remember, it's a ratio that you have to say 1 mole of this and nitrogen atoms to every 2.5 moles of oxygen atoms, and 2 moles of nitrogen atoms to 5 moles of oxygen atoms is the same ratio, right? So all we're doing is we're just converting these into whole number ratios because we can't have a half an atom, right? So all we're doing is making it a whole atom by multiplying by a factor. So we have 1 mole of nitrogen atoms to 2.5 moles of oxygen atoms, but in reality it's really 2 moles of nitrogen atoms to 5 moles of oxygen atoms. Now, in the case that you get a different number here, let's say you get 2.33 or 2.67 or something like that, the factor you'd have to multiply by is not 2, it would be 3, because 3 times 2.33 is 7, and 2.67 would be 8. So here are the factors that you would use. If your subscript ends in 0.33 or 0.67, everything gets multiplied by 3. 0.25 to 0.75, everything gets multiplied by 4. 0.2 to 0.8, 5, things like that. If it's under or equal to 0.1 or lower, then you're going to assume that that's close enough to the nearest whole number. So 0.9 would be 1, 1.1 would be 1. Okay, so what you're going to do now is you're going to practice. So stop the video when I tell you to, copy the information down, tell me which one of these is the correct empirical formula based on 40% sulfur and 60% oxygen by weight. So stop the video now. Alright, so here are the answers. Hopefully you got the same answers as we did. So 40 grams, when I convert that to moles, I get 1.25 moles. 60 grams of oxygen, when I convert that to moles, that's 3.75. 1.25 is the smaller of the two, so I divide through by 1.25 to get this to be 1. Fortuitously, that became a 3. So my ratio is 1 mole of sulfur atoms for every 3 moles of oxygen atoms, or in a compound, there's 1 sulfur atom for every 3 oxygen atoms. And that's what you got here. So again, if you have any questions, follow up with me.